Hey, I think Akash is also here. Hello.
Hi guys. Hello. Hello.
We're doing an in-person breakdown of Transformer for TSFM. And in a way, the goal is to make basically like if you were there for lectures one and two, the in-person lecture three was just too dense. So the goal of this recording is to basically like break it down in a way that's compatible with how lectures one and two were structured so that the transformer makes sense. And then we can like talk about um, the lecture three content itself, which is like, oh, why does rope work as well as it does? And what is the role of FFNs and all of these things. But before all of that, we need a precursor, which is like diving deep into transformers and what they are and why they're powerful and what is the motivation for building them, etc. Uh, yeah. So yeah, should I just like start start talking and then
Sure. Yeah.
yeah. At any point, if any of you guys have questions, you should just like interrupt me. That's the goal of this session, to be doing this like at a much smaller scale so that we can constantly like stop, take a sidetrack, explore something, talk about something, and like come back to this so that people who are watching this would find it useful. Um, so we have uh, yeah. In lectures one and two, we talked about the framework of learning and tokenizers. Uh, and the tokenization scheme itself was what we were talking about was let me open Canopia. Uh, yeah. Yeah, we basically talked about how we want to construct a dictionary for uh, yeah, for the alphabet, right? So we want to transform text that is symbolic and discrete to something the world of numbers can understand, which is why we started with, okay, let's just have these dictionary mappings which map these characters to a vector of numbers, which are initially randomly initialized. But over time, over the course of training, they will we will tune those parameters, tune these vectors to capture the meaning of the alphabet here. But then again, we discussed that like the granularity doesn't need to be A, B, C. It can be like phrases, it can be sentences, it can be entire documents. And we, in lecture two, we discussed the trade-offs for each of them. Whether we want to represent, how do we want to represent text to the model? Is it through a series of characters, through a series of words, through a series of bytes, and so on? And we settled on these subword representations that are learned through byte pair encoding. So what that means is like the keys of this dictionary, instead of being ABC, would be subword representations, which we call tokens. So, so in the transformer, the very first layer, before we even talk about the core architecture itself, the very first layer is the positional embedding layers, which is basically the layer that transforms these tokens, whether that's A or something like uh, you know uh, Toronto, or and sometimes it can be space. True that. I don't know. So it can be anything. It can be tokens that are learned through white pair encoding. And after, if you've done the assignment for lecture two, you probably ended up with a vocabulary, right? Like with maybe 20,000 tokens or 10,000 tokens, depending on how many iterations you ran the merging algorithm for. So how many ever tokens you end up with in your vocabulary is how many keys there will be in this dictionary. There would be like 10,000 keys, and all those keys would map to like initially random vectors, which again tune themselves. So the very first layer in a transformer is actually just that. It's actually just this dictionary where it looks at all the bytes or looks at all the tokens that are, and then converts them into these numbers. So if there are like, if your sequence length is like 5 tokens, uh, can change the. Yeah. If your sequence length is 5 tokens, then your first layer would be like, let's say I am a good dog. That's like 5 tokens almost, because maybe we can assume that I am a good dog, just like tokenizes like word-wise, and this would convert into a vector of numbers, and this would convert to a vector of numbers, this would convert to a vector of numbers, and so on. So in the end, what you have is basically a matrix of 5 rows by how much ever the dimension of this vector is. And that is basically what we call the embedding dimension or the hidden dimension of the transformer. It can be 1024, it can be 512, it can be anything, basically. And there are some hardware considerations when you're deciding on the embedding dimension, but we'll get to that later. But for this, let's just say your embedding dimension is 128. Okay, so what you have after the tokenization and after the very first layer of transformer, which is the uh, positional embedding, sorry, not positional embedding layer, but like the token projection input embedding layer. So the input embedding layer, so that would be like maybe you can call this x1, x2, and so on, x127, 128, and then you can call this let's just say 1 and x1, 2, x2, 2, so on, x128, 2, and so on, x5, sorry, x1, x2, 5. So this is the basic atomic matrix that the rest of the core transformer architecture operates on, where each row corresponds to the vector representation of the token that corresponds to our sentence. Okay.
So I have a question there.
Yeah.
Are there any best practices when we're curating this data set, or we'll cover it later? Or so this has to be all text, or all logical text, or all code, or
So we'll discuss that in like data, because usually like when I say, oh, we're scraping the entire internet, it's like it's basically we're trying to also curate. It's a balance of like, okay, how most of the internet is just like really junk text. It's not really useful to model the web. So what we want is like subset of things. So usually what people go for is like people scraped Reddit. Reddit is huge and it's all humans, at least before AI. And so the way they filtered is like they scraped all of Reddit and kept anything that is like at least has 2 upvotes or something. And same for Stack Overflow. Stack Overflow is like a Q&A format. And like even code is like high quality because people are writing code. So you scrape GitHub and all the repos and process it. So you do want high quality data, but you don't want your bar for quality to be so high that you're discarding most of your. At pre-training, you want to diversify. You prioritize diversification, but not too much at the expense of quality. But
Okay.
but obviously, like you
so
have
that's a
to.
separate topic.
Yeah.
But for today's session, it is just byte stream, or the
Tokens.
tokens.
Yeah, tokens that map to these vectors. So in this case, it's 5 by 128 because we have 5 tokens and I'm a good dog, and each token corresponds to 128 dimensional vectors.
I have a question about like different models use like different tokenizers, vectors.
Why do different models use different tokenizers?
Yeah. Why not like use one that's like different? I guess I don't know.
It's in a way, it's like very people now use like very standardized tokenizers. Maybe they just use GPT-4o's tokenizer to train like a different model. But to begin with, like everyone was doing it their own way, and you maybe want to train your. Okay, for example, Cohere had its own tokenizer.
Yeah.
With
what would be the benefit?
255,000 tokens, and for its time, I think everyone like GPT was 50,000 tokens vocabulary size, and Cohere's vocabulary was 5x. It's 5 times that. And why is that? Why does that make sense? Because like one of the core priorities at the time for Cohere was like doing multilingual training and making models that are multilingual. And one of the side effects, or like it's intentional, but one of the side effects of expanding your vocabulary that much is that you can get away with uh, producing fewer tokens for like other languages. So if you're overloading if you're saying my vocabulary is only 50,000 tokens, maybe most of that is focused on like English, like efficient English representations. So anything that is not English, or like that is not heavily present in the training data, that means that you're basically representing those as bytes, right? Like we talked about like how BPE is basically like Unicode format, and Unicode represents each thing as like a byte. So if the language model is not, it doesn't have a token corresponding to the like a Telugu word, for example, like that's the language I speak, and Telugu word, for example, then it basically is going to view that word as a sequence of characters, and each sequence of characters, like each character could be 2 bytes because it's not English, right? So in Unicode means that it will have 2 bytes. So if there are 5 characters, then I'm suddenly decoding 10 bytes. So it's like 10 decoding steps. So at serving time, when like you're serving your language model, your one word Telugu text requires 10 decoding steps. While if you train like your tokenizer with with a huge vocabulary size, with a heavy emphasis on your training data, you maybe only have to decode for three decoding steps. I'm just like creating numbers right now. Like so that's the idea, that you want to trade off how many decoding steps you would need for serving time, depending on your demographic, or like what's your focus. Yeah.
So
Makes sense.
in inference, there's like a process of like tokenizations and detokenizations. So you can think of it as like, oh, first you have all the text, you have to convert it to like tokens. And then your models will operate on that tokens, and then it would output like a new list of tokens updated, with the current text that you have, plus the tokens that the model generates. And then you have to sort of like do the process of like detokenization. So basically converting that list of like input ID back into text. So in a sense, the detokenizations are on CPU, but it's mostly like an inference thing as well, where you want to scale the detokenization and the tokenizations separately from the actual running of the forward pass itself, because you are essentially moving data from CPU to GPU and back to CPU. But yeah, that's the idea of like, oh, if we have like a better tokenization, then that step can be optimized like very well as well.
Right. Scale. Interesting. Thank you so much.
Yeah. Okay. So that's the very first layer of transform, which is basically like a dictionary lookup, which people represent as one-hot encoded vectors, or directly like lookup operations. So putting that aside, we fundamentally have this willingness to build a system that understands language, which means now we are tasked with, okay, how do we actually build this? We have the vector representations, even though they're randomly initialized, and we'll tune them. But what is the main model that sits in between and processes the information? And what is the output of this model? That's the question we want to ask, right? So basically, like, this is the model, and it takes in variable length text, and does a series of predictions. And now we can ask the question, like, what is the series of predictions that the model is making? Yeah. So again, from lecture 1, we decided that we have a bunch of data, which is the variable length text, which is coming from the internet. And we have the model, which actually makes predictions. And we have the signal that we measure. Basically, like, okay, how far off are you from the target? Right? Like, are your predictions correct or incorrect? So which means even before we decide on the model, we are trying to say, okay, what is the prediction that the model is trying to make here? How do we even craft this target signal. And that brings us to the next token prediction stuff. So one of the big issues in machine learning is basically if you have data, how do you construct the targets? Because it's very rare that you keep finding data, like tons of data, where you have like the explicit ground truth. Like take biology, for example. If you're trying to build like a peptide that is very effective against like maybe cancer, and you want to quantify that, okay, this peptide is better than the other, this peptide is better than the other. It's not an easy thing to find because like you have to run experiments and actually like uh, validate it experimentally.
Right.
So that supervised data is hard to find.
Right.
So people have to come up with clever ways to basically like create a target. And in this case, like it's kind of intuitive to say, okay, if I have a series of tokens that represent text, why don't we just like make the model look at like one at each time step, or like why don't we model predict the next word or next token? So in this case, I want a dog. Sorry, that was not the thing, right? What was the thing? I'm a good dog. I am a good dog. So the way we like came up with to process this information is basically, okay, let's decompose this into a series of tasks where the model first looks at the word I and tries to predict am. Predict am.
Okay.
And then the model looks at the phrase I am and tries to predict the word A, or the token A. And then I am a, and it tries to predict good. And then I am a good.
So when it's predicting the next token, it has some memory of tokens which came before.
Yeah, exactly. So it's basically like, so if you have these 5 words, it's decomposing this into 4 tasks, where each of these tasks is basically like the first word predicting the second word, the first and second word predicting the third word, and the 3 words predicting the fourth word. So that's how people were like, okay, this is how we're going to train the model, like construct the targets to train the model, because we know what's going to come up to the sentence. We know the full sentence, how it's structured. But if we show the model only like a group of words at a time, because the model has no information about what's coming next, we can make the model predict that next word and say, hey, like this is the actual next word and this is the prediction you've made. So please correct yourself. And we propagate that signal backwards and tune the parameters so that the model keeps making better predictions.
Yeah, I would just like if there's something, the temperature, etc. Right?
Yeah, like that we don't even have to worry about it.
Okay.
Like we can just pick the R max sampling, which is like okay, you make the model predicts a distribution of output tokens, say, assigning a probability to each, and you just pick the token that has the maximum probability.
Okay.
So, but is this clear? The next token prediction task, like
Right.
Yes.
and that's how we predict the target, and then or that's how we construct the target. So this is basically what it is doing. Is like if you look at it as like a probability distribution of like a sentence where you have token 1, token 2, token 3, token 4. So if you know like the probability chain rule, which is basically the decomposition of joint probability, what this is saying is like you basically are computing P1, P of probability of T1, multiplied by probability of T2 given T1, and probability of multiplied by T1, T2, and then multiplied by probability of T4, T1, T2, T3. So the joint probability of any sequence of events is basically you express this as conditional probabilities.
So if you have predicted last 4 words correctly, the probability of predicting next word is going to be very high. Yes or no? Oh, I'm lost.
If you've predicted 3
last 4 words correctly, the probability of predicting the next one is going to be very high.
You can say that if the model has learned like how, yeah. Okay. So this is just like a probability formula of like expressing the probability of multiple events occurring together and expressing them as like a sequence of, okay, if this event has occurred, what is the probability of this event occurring? So it's like decomposing that. And mathematically grounding this, like this is basically like how we train language models. By if you apply logarithm on both sides. So we have log p, t1, t2, t3, t4, and we have log of this entire expression, right? Is that clear?
Yes.
Yeah. So logarithm of products is basically sum of log probabilities. So log a times b is log a plus log b. So what that translates to is log of pt1 plus log p2, t2 given t1 plus so on. So this is the task that we basically want to measure. Like, what is the log probability of this document occurring as it is seen of the sentence? And we want to maximize that, which means we want to maximize this sum of probabilities. This sum of conditional probabilities. And if you notice the structure here, then we are basically looking at what is the probability of T2 given T1, and what is the probability of T3 given T1 and T2, and so on. So that's basically like the next token prediction, right? Because what this is basically telling us here is if you're looking at tokens T1 to T3 and trying to predict T4, and then you're looking at tokens T1, T2, and trying to predict T3, and that's the probability distribution you're trying to model. And that's how transformers are trained too. This series of log probabilities is phrased as like cross entropy task, and then we like backward pass, we backpropagate that loss throughout the mathematical model. Okay, so that's how we are constructing targets. We have the input embeddings, which are basically token to vector mappings, and it goes through this abstract mathematical model, which we don't know yet. And the model makes predictions, and the kind of predictions it is making is basically this next token prediction, where each token is looking at everything that came before it and itself and trying to predict the next token. And that's what this is doing. Okay, so now we talked about the very first layer, the input, and how do we translate tokens to numbers. And we've talked about how we construct the target itself of doing the next token prediction. And now the question becomes, okay, what is the model that's making these predictions? And how do we actually implement this causal structure of like each token can only look at itself and the ones behind it and not ahead, you know? Because if the model is able to look ahead, it's basically cheating because it knows the answer already. So how do we actually enforce or mathematically ground this whole process of like, okay, this next token prediction, and each token being able to look at itself and the tokens before it. So that came up in the 2017 like transformer paper. There were ideas before this as well, like to do just like causal language modeling, but today we're just going to talk about transformers. So after the input embedding layer,
Quick question.
yeah.
Most model are causal, right? Or I guess there are maps, but most decoder only transformers are
Causal. Yeah, like almost all of the LLMs you use are like causal.
Yeah.
There are embedding models that are basically bidirectional. They look at everything.
Yeah.
But yeah. And we call this kind of autoregressive because the model is kind of unrolling, right? It's looking at one token, trying to predict the next token, and you take that next token, and now you have two tokens, and now you're predicting the next token. It's basically a series of next token prediction tasks. Any questions?
No.
Okay. Okay. And now we have the model itself. And we can switch to Uh, and this is what the transformer architecture looks like. We briefly talked about it last week, but we'll go into detail a little bit today. We talked about the input token vectors, which is the input embedding matrix. And we talked about the output token vectors, which are basically like, in the end, what you have is like, here the 500 and 128, 5 by 128 matrix that we talked about, like 5 tokens having 128, each token having 128 dimension vector representation. The output token vectors are also of the same shape. It's like 5 by 128. And now you want to transform this 128 hidden dimensional space into like a probability distribution over the entire vocabulary. So which would be hopefully you can see this. So if your input to the transformer is 5 by 128, then it goes through the model and comes like a more meaningful representation of the same shape, 5 by 128, 5 rows, 128 columns. And now you're saying like to actually make the predictions of what is the next token, right? So you need to convert at each time step. You need to convert the output of each time step to basically a bunch of predictions over the output token space. Does that make sense? So you seem a bit lost.
I'm thinking about something right now. Yeah, it's it.
Yeah. So you see this, right? I is predicting I am, and so on. And to the model, there are 50,000, if let's say your vocabulary is 50K tokens, there are 50K possibilities here. Hopefully our model picks like am instead of something else,
Okay.
but there are 50K possibilities at each time step that it can predict any of the tokens as the next token. 50K, 50K, 50K. So when we are processing this word, we basically have these time steps, each predicting a distribution over 50,000 tokens, saying that this is like the probability assignment. And so what that means is that we are transforming this 5 by 128 matrix into 5 by 50K, where like each token now, like each row represents, for let's say, like for this example, I am a good dog. The first row represents the word for the token I, and then you have 50,000 values, and all those 50,000 values correspond to the scores of like what the model believes. Maybe this score is the highest by saying it's like S3, and this is S1, S2, and so on, S50K. And maybe the model says, okay, S3 has the highest score. The S3 corresponds to a token as well, because it's like a part of the 50,000 sequence. And so S3 maybe corresponds to the word am. And then we know the model is right, because the highest score was S3, and the third position is actually taken up by the token am. And if the model says instead, oh, I'm actually going to predict, so let's say for the second row that corresponds to the word am, then what the model predicts S1, S2, S3, and so on, S50K. So these scores now correspond to like, okay, I've looked at I and am, what is the next word? And that's what these scores are trying to say. So maybe the model says, I'm going to pick S49 as the highest score. But S49 at the 49th position in our vocabulary of 50,000 tokens, our 49th position is actually taken by, let's say, guitar. And we know guitar is wrong because we know the initial sentence is I am a good dog. So the next prediction should be corresponding to the token instead of guitar. The model assigned highest score to S49, but maybe it should have assigned the highest score to maybe S1, because the first position is taken up by A. So we know the model like messed up.
Yeah.
And we need to extract that. And that is basically the output token vectors here. So we are going from 5 by 128 to 5 by 50K. And to make that happen, what we basically have is like, the way to look at it is like matrix multiplications are a tool. Like are a tool whenever you want to project from one dimension to another dimension, you do a matrix multiplication, which is like a feed forward, like it's like a linear model. In lecture one, if you remember, we talked about linear models, and a bunch of linear models is basically like a matrix multiplication, where you're transforming this 128 dimensional space into a 50,000 dimensional space. So what that means is like you have the output embedding matrix. Output embedding weight matrix that turns this 128 dimensions to 50,000 dimensions. So which means your weight matrix is actually of has 128 rows and 50,000 columns. So now when you have the final output from the transformer is 5 by 128, call this matrix A. And you have matrix B, which is the actual weight matrix, which is of shape 128 by 50,000. So this is B. And the matrix multiplication of these two is basically like, this is the dimension M, this is the dimension N and K, and that gives 5 by 50K. So your output embedding matrix is 128, which is the hidden dimension, by it has 128 rows and the number of vocabulary tokens columns. So now we figured out, okay, there are the input token vectors, which are basically dictionary lookups, and the output token vectors, the token classification head here, which we can also call as an output embedding weight matrix, which projects it into like a prediction space of like 50,000, assigns 50,000 scores and that. And now we can like talk about the model of like, how do we actually implement this thing? Any questions so far? Is this also too trivial? I can also like try to speed up. Like
Yeah.
I would say it's good, yeah.
And the speed is okay. I think we need the speed.
Okay.
Yeah.
And now for transformer, we have a bunch of decoder blocks. So any deep learning architecture has a bunch of layers, right? So it's layers stacked upon layers, and that's why it's called deep learning, because you're stacking multiple layers, and hopefully each layer picks up. As you go deeper into the network, you're picking up more and more complex information, complex patterns in the input, whether that's images, text, videos, whatever it is. That's the idea, that like you have a single layer that has some representational capacity to learn stuff. So in lecture one, we talked about matrix multiplications and linear models, where we were trying to build a model that predicted like a straight line. And then we went to a model that was predicting like a 2D plane. And now we are getting more and more complex. So we are not just restricting ourselves to that 2 dimensions or 3 dimensions. We are going to thousands of dimensions to capture that representational power of this like n-dimensional domain, like matrix algebra. And you have like a single layer that has some representational capacity, but you have the repetitions of the same layer. So there's a layer 1, layer 2, layer 3, layer 4, and hopefully as the vectors propagate throughout these layers, you pick up on information and patterns, and hopefully you understand the domain that the model is being exposed to. Okay, now let's not even talk about position membranes because they're not necessary. Here you have a decoder block. Decoder block is actually just the transformer layer. And the transformer layer has this structure here. So we have layer norm and masked self-attention, like residual connections, and layer norm and FFN again, like FFN. So this stands for feed forward network. This is for layer norm. This is masked self-attention, layer norm. So let's look at first, so the layer norm and residuals we'll talk about later.
So this is one, sorry.
Yeah.
This is one decoder block.
Yeah.
You can have multiple decoder blocks stacked.
Yeah.
like this. What purpose are they serving?
Of what is what, sir?
Like this layer
Layer.
of recorded block.
So like stacking layers on layers.
Yes.
That is what, like, hopefully when you stack layers together, you pick up increasingly complex abstractions. So basically, it's like a hierarchy of representations and abstractions. So maybe your very first decoded block is saying, okay, I understand the that like letters have to be arranged a certain way to have words. And the second layer is like, okay, so maybe words have to be arranged a certain way to form valid grammar, which is basically like prepositions and verbs, adverbs, and all of that. And third layer is now picking up more complex stuff. Maybe you're saying, like, okay, grammatically it's correct, but is it like, does this make sense? Like, do the semantics make sense? Oh, this is so we talked about briefly in lecture 3 with FFNs of like, oh, layer 1 is looking at whether a sentence ends with the word substitutes, and layer 16 is talking about TV shows.
Yes. Yeah.
You know, so all of these are like increasingly complicated patterns. So that's the hope when we stack layers on layers, that the model, as it gets deeper, when the information in the deeper layers, that is actually representing something more complex and abstract, so that it can use the lower level abstractions and slowly build on them.
So for a given problem, how many layers we need? How do we decide that?
That is just empirical
Experimentation.
experimentation. Like, you just look at a bunch of metrics and you say, okay, let's start with like maybe 12 layers and all that. Yeah, it's just mostly empirical science. The field has settled on.
Yeah, if you want to know like the motivation behind it, I think like the paper Work to Effect by Nicola in 2013. So like go into the behavior of like why like stacking layers so like works. Well, more of like I guess tokens in embedded space, but ideally if you build more layers, you build like a more complex representations of types in a multi-dimensional vector space.
Okay, so what would be the norm of like number of like layers and scale to like enterprise level? What would be the norm?
I'm sorry.
What would be the like approximate amount of like layers at like enterprise level? So
It completely depends on the use case. Like, it's not even a question of like, oh, whether you're building for consumers or enterprise.
Oh.
Then you're asking, like, what is the purpose of this?
Okay.
And if you're trying to build like systems that understand language generally and have some notion of world knowledge and all the things that when we describe, we intuitively understand, then that's basically a whole range of concepts that the model needs to learn. Right. So then, like, you're saying, okay, this model needs to be deep, it needs to be large, wide, and saying, okay, it's all you're thinking in terms of representational capacity. And you have, this is a series of experimentation. So there are like use cases for enterprise. Maybe it's just like an editing model, and it takes like an input text and like edits it to make it look nicer, or like formatting models. And those models can be a lot smaller because they're not burdened with, okay, I need to understand what the content itself is, but maybe like with editing you can get away with like smaller capacity, so you don't need big models. So it completely depends on the use case and what kind of model that you're trying to train. With LLMs specifically, when we say that, oh, we are modeling the web is basically, like when I'm thinking about something, I just like write it on the internet. I write blogs of like, oh, about the human condition or about music or about whatever. So that's just for me. And like everyone has their own niches and like writes things. And so basically what you're saying for an LLM when you're asking it to model the web is like, just somehow capture and understand all of these vast range of concepts that humans are putting out there. And that's like a really huge task. It's for like mathematical models to capture. So then maybe you say, okay, we need big models. We need like a trillion parameter model to make like something that's smarter than anyone else, because it's like the aggregation of all human information. Yeah. But anyway, like at the fundamental level, it's all experimentation. You try it, does it work? No. Go bigger. Does it work? No. Then go bigger even. If it doesn't work then too, then maybe you have something buggy in your experimentation. So you just like like I said, it's like an empirical science. You come up with ideas, you run the experiments, you validate them, learn from them, and you just keep iterating.
Right. Yeah, so you've mentioned some like metrics earlier, like all first the experimentation, all the metrics that like just a breakdown of metrics that engineers produce. But like what about this?
What metrics can you like? There's this metric called perplexity, and even validation loss, which is basically cross entropy.
Cross entropy.
yeah.
Okay.
You can look at those, but again, benchmarks are useful. They're important. Like you have this task called MMLU, where the field was obsessed, for example, like recently. So it's called massively multi-task language understanding.
Yeah.
So that's basically like a series of multiple choice questions spanning many different fields or disciplines. So over the course of pre-training, most of these models have actually like seen that information. So if you're testing for MMLU, you're basically testing for, okay, how much of the knowledge that you've seen over the course of your training do you retain? And can you answer? Do you understand the formatting of MCQs? Do you understand the concepts being referred to here? And can you recall the information that you saw during training and say and apply that to this question? So yeah, you have different benchmarks.
Like recall, right? Yeah. Like accuracy, recall. I think it's also
Yeah. F1, F2.
like F1.
Yeah.
Okay.
All those.
Yeah, if you have any classification tasks, you can bring those
Yeah.
metrics up. Yeah.
Okay.
One quick question.
Yeah.
So I'm thinking in terms of chinchilla paper and the scaling loss paper.
Yeah.
Where performance improves with compute and data.
Yeah.
Now, data will be the input token vectors.
Yeah.
We increasing that.
Yeah.
Compute is raw compute or the number of decoded blocks. I think it is raw compute.
Yeah, you can say it's a number of decoded blocks. Yeah, but I mean, it's also talking about how many training steps you're doing. But when you're doing this, we'll maybe do some arithmetic models right now, like right now as in over the course of this lecture. But yeah, compute as in it's like a calculation of like what each block is doing, how many flops that is, and how many training steps are you running for. Okay. We'll look at these things individually. Okay. So layer norms and residuals, it's almost like I cannot explain it because I don't have, like, I can tell you the reasons, but I cannot prove to you that this is actually makes perfect intuitive sense and this is like what we settled on. But let's start with attention. And the core concept of like attention is that you have, again, a sentence, and the intuition is that each word in the sentence doesn't stand on its own. I gave an example in lecture 3 where I said, these chips are really well designed. That was the example, that's the sentence. And to really capture the essence of the statement, you need to understand the context in which this sentence sits, or the word chips sits, right? And if you see this in a blog that talks about semiconductors, like semi-analysis, then you know this is talking about computer chips. If you see this in a blog that is from a food blogger, then you know like this is talking about like edible chips, right? So what you take from that is that each word is not just sitting on its own. It's not an isolated thing that you can completely understand by analyzing it like almost atomically. You have to look at what came before it. What is the context in which this word sits to really understand or represent it well? And that's kind of attention mechanism. And attention itself is not novel to 2017 paper. Even before this, computer vision used attention. But like this form of self-attention that we'll talk about is like novel to this paper, like multi-headed self-attention. But even that you can just like tweak and draw various analogies to the prior work, and yeah. But let's look at what that would look like if we were to ground it of this intuition, right? If I'm saying that every word depends on every word's true essence can only be captured through everything that came before it, how do you express that? So let's just say there is a sentence, which is the chips are into. Okay. Yeah. So the sentence, the chips are okay. Let's just look at a solution. Okay. I don't remember the correct figure. Does anyone remember? Do you remember how many flops H100 has?
H100.
Yeah, 295.
If we, I guess like if we're doing like FP16,
Yeah,
it's like 48.
48.
Like yeah.
That's funny.
Wait, or is it 20?
I think it's much higher.
FP.
BF16.
Oh,
BF16.
I have a number actually.
I think it's something like 270 or 300.
So is it, yeah, can I plug some just
Yeah, go for it. Okay, 1980 teraflops.
1989.5
Okay.
teraflops of FP16.
Has, let's say 1900 teraflops. These chips are really well designed. So this is the sentence that we're looking at. H100 has 19 teraflops, and like these chips are really well designed. So for the intuition to make sense and for us to like formally ground it, we can say that like, okay, if every sentence, if every token in this sentence is a combination of everything that came before it, because we are still trying to do like next token prediction, then you basically need a matrix that represents the scores, the pairwise scores of everything that came before it. Does that make sense?
Mhm.
Were you able to plug your laptop in?
Yeah, I'm good.
Okay. So let's say this is token 1, token 2, token 3, token 4, and this is token 5, token 6, token 7, 8, token 9, token 10. So now what you have is what you want to pick to represent that intuition. Do you have ideas for how to do that?
The correlations between the two.
Yeah.
So I guess
Or-
n by n matrices and
Mhm.
to find the distance between, or I guess cosine similarities between two tokens.
Yeah, that's a good idea. You guys have any ideas?
Can you repeat the question again?
We have like
You have the sentence and
then like the question is basically like there is the intuition of you want to like you want to express each sentence, like each word in a sentence as like a combination of everything that came before it. And how do you formulate this idea of like each token being everything, a combination of everything else? And we can just do like assign scores.
Yeah.
Right? Assign scores to each word in the sentence. So let's say this is T1, T2, T3, so on up to T10. And we are saying that.
But I have a question. Like
Yeah.
if there's something, there has to be some memory somewhere who's keeping track of like what it's want and what it's want to predict.
Mhm.
And that system will assign the scores or pick something. I'm not sure, I'm just blabbering maybe, but
Sorry, go for say again.
like for any system to predict a sentence, there has to be some let me form my thoughts, I'll come back to you.
Okay.
Let's continue with this.
To ground the intuition, we are basically saying, okay, each word is a combination of everything that came before it.
Hmm.
So let me assign a score to every word that came before me and myself. That's the intuition. So T1, this is the sentence we are looking at, right? You can see the screen. Right?
Yeah.
Can you read it?
Yeah.
Yeah. Okay. Let me know if you want me to zoom in or something.
That's fine.
Yeah. So T1 is H100. So there's nothing that came before this word in the sentence. So you assign a score, maybe S1. And T2 has like now, okay, this is T1, T2, T3, so on, T10. So this is 0, 0, so on, 0. And why is it zeros?
Because it hasn't, I guess, it appeared yet, right?
Mm-hmm.
So in a sense,
Yeah.
you do the score between T2 and T1 because T2 has not appeared yet, then essentially that's would be equal to 0.
Yeah. So there's nothing that came before T1. And like the H100 cannot look up, cannot look ahead, because again, the fundamental is like we want to do next token prediction. Right. And if H100 has the ability, like the token H100 has the ability to look ahead and say, oh, the word after me is has, that's basically cheating. It's not learning anything because we are showing it the answer and saying, hey, what's the answer? That doesn't make sense. So this is by construction invisible to the first token. The second token is invisible to the first token. The third token is invisible to the first two tokens. And now if we want to assign scores to this, right? So for T2, the word has score, like T2 can see T1 and T2. So it assigns another score. And its score, maybe it says S1, S2, 1. And everything is again zeros. So now this is saying, okay, for T2, which is basically has is a combination of, I'm giving this weight, S1, S11 to the word H100 and S21 to the word has, like to myself. And that captures the true essence of the word has, and so on. And ultimately you have T10, which is designed, and you can say S1, 10, S2, 10, S3, 10, so on to S10, 10.
I guess a quick question is that I thought that for calculating like attention matrices, if we don't enforce any sort of mass, right? In a sense, every positions on that matrix should have a score, right? So even when you do S1, it wouldn't be necessarily 0, but like I guess like I was
You're talking about these elements?
Yeah, like because like the elements that like on the
Yeah.
upper triangle, right?
Yeah.
Technically, it should also have.
Yeah, it should have elements.
It should have.
Yeah. There are associated scores.
Right.
But by construction, we are explicitly zeroing them out.
I see.
Because we don't want to like say.
So this is essentially the causal mass.
Yeah, the causal
Right.
mass.
I see.
Yeah.
Okay. Makes sense.
Does the score matrix make sense for in terms of the intuition? If you're saying like
I'm a little lost. Like,
Yeah.
why are we doing this? Sorry.
Yeah. So you understand the intuition, right? Like I told you the intuition.
Like,
And-
which component is this, and what are we trying to like?
Yeah. This is we are getting to attention.
Okay.
And for attention, we are basically like if we were to ground this intuition in like mathematics and say, hey, like if each word is a combination of everything that came before it, let's assign scores. Yeah.
Okay.
So let's assign scores. So then the word designed, so the true value of designed is equal to S110 times true value. I'm just gonna say TV of token 1, TV1 plus S210 TV2 plus S1010 TV10. So basically it's a weighted combination, weighted by the scores that this matrix contains. It's a weighted combination of the true values of every other word. That's what we're
Weights, right?
I'm sorry?
Like weights, right?
The weight is the score in this matrix.
Yes.
Yes.
Yeah.
Okay, so how is it helping us? Like,
Yeah,
weighted sum?
because it's giving us like more meaningful representations because we have this intuition, and then now we basically like gave it a mathematical formulation of like how do we actually combine information of different tokens in a sentence and express each token as a combination of all the tokens that came before it. And this is what that is giving us.
Mathematically.
Yeah, it's giving us a way to actually express a single vector as a combination of all the other vectors that came
Oh, got
before
it, got it, got
Yeah.
it.
And that is basically the essence of attention operation. That is all it is doing. And the way like the query key values, all of these are basically trying to get to this stage. And okay, so let's actually look at the attention operation itself now, how it's constructed. So you have the initial 5 by, or like I'll just start using symbols like the notations.
Yeah.
So let's just say the number of tokens that you're processing, num tokens, is n, and your embedding dimension is d. And so what is the shape of the matrix that would be incoming to the transformer?
Embedded. Embedded.
N by d. So now your attention layer initially receives an input of receives an input matrix of shape n by d, and now you're branching out into three terms. You have the x, which is n by d. And these are like the query key values of the attention mechanism. So you have a query that again you can view attention as like basically like a dictionary mechanism. And you have your query, you have a key value dictionary pair, and you want to query this key value dictionary pair using this query matrix. That's what's happening.
So all the information is stored in FFN.
We are not at FFNs yet, yeah. But
Yeah.
The querying part is controlled here.
yeah, like the entire query part is even controlled through QKV.
QKV. Yes.
Yeah. So, but there's a nice intuition around attention itself, which is like the KV are like so the represent. It's called self-attention because all of these terms are operating on the tokens themselves.
Okay.
You know, like yeah, we'll see that. So we have this n by d matrix that's being projected to query key value parts, and there's this thing called multi-headed attention. So we are doing attention actually on n number of heads, but let's just like simplify that.
How many types of attention are there? So self-attention is one, or multi-head is another one.
So there's multi-head attention, and there's like efficient variations of that, which is like GQA, like grouped query attention, and there's MLA, which is multi-latent attention, and there is what else?
MFA more. That's like a new one. They call like multi-factorizations attention.
So this is a very well-established concept in ML deep learning, and we are just using this particular type of.
Yeah, I mean the 2017 paper introduced this
Yeah.
the transformer paper. Okay, so yeah, let's just forget about multi-head, but let's just talk about a single head. And before that, okay. So attention. We have like this n by d matrix, and now we have to create three other representations of the same matrix of also of output shapes n by d. Let's not worry about multi-head attention yet, but n by d, n by d. Okay. Now what is the matrix shape here? Because now everything is parameterized by weights, like in transformer, right? And if we're saying that we have these query key value projections what should be the shape of the projection that takes us from n by d to n by d again?
Dash line sequence length and did.
I'm talking about this edge here, like the projection.
Oh,
So,
like
yeah.
the H. So we are doing n by d to n by d.
Yeah. So we have like an n by d matrix,
Right.
and we are transforming these d dimensions back to like just d dimensions.
Oh, I see.
Yeah.
So that would just be n, right?
That would just like I mean, we were trying to talk about like the query key value projections.
Okay.
So that weight matrix would be
Right.
just like d by d.
D by d.
Yeah.
Yes.
Uh,
Or d squared, right?
Yeah.
D by d, right? Because we.
So we have WK, WQ, WK, WV. You know, these three weight matrices that take us from a d-dimensional vector for each token into another d-dimensional vector, which is like represents Q, K, and V. And now the actual attention operation is basically it's using these QK terms to compute the score matrix here that we talked about, this matrix.
Oh, the one we talking about.
Yeah. So we are saying this is n by d, this Q, and K is also n by d. And now, how do we come up with this core matrix, which is like n by n shape?
We transpose it, right?
Yeah.
Yeah.
So we do a matrix multiplication
Yeah.
of the query matrix multiplied
This is
by
the actual attention operation.
yeah.
Okay.
So this is multiplying the query matrix by the transpose of key,
Okay.
which is basically giving us like an n by n score matrix.
Okay.
Yeah. So this n by n score matrix is basically this.
The variant matrix which we wanted to.
Yeah.
Okay.
Yeah. So this is giving us the score matrix, and then we do like for like math. We don't have to talk about the reason right now, but this matrix multiplication is divided by square root of d. And that is to control the variance of the matrix multiplication. And you can do this if you have like some stats background. You can look at like what happens to the variance of like if you multiply two matrices, which are just like sampled from a Gaussian distribution, you can look at the variance of the output because the inner product is along D. So D is the dimension that's getting squashed and given to n by n matrix, and that D is actually going to have like you're summing up these D elements, each with a variance of a certain element. So then the variance is actually going to be like
very big.
Yeah, D. So the standard deviation is square root D, which is why you're dividing this matrix multiplication. So you have like now these n by n scores, and now you want to convert this into like a normalized vector here. So you have like I said here S1, S1, S11, S12, and so on. So you want these scores can be unnormalized, right? One of them can be like 19 or minus 25 or something like that. So you want to convert this into zero to like a basically a probability distribution of like you're saying, okay, this is like let's just say we are talking about the 10th vector. You're saying, which is basically okay, what does design depend on? Design depends on every other token. So maybe I'm saying these chips are really well designed. So I'm just saying maybe this has probability of 0.1 or like value of 0.1, and this is 0.1, this is 0.2, and so on for maybe this is 0.3. So the total sum is 1.0. Okay. So then you do basically like a softmax operation. A softmax operation is basically like a normalization operation. It's like it has its own characteristics, but it's basically if you have a vector of v1 to vn, then basically it's like e power vi by summation dvj all j, and that is the vector. So you're transforming each element into like basically exponent of e1 plus ev1 e2 evn and then e power v2 so on and so on. Why do we do this? Like we don't have to go with softmax, and there are variations where people get rid of softmax altogether, and then that takes the form of like a recurrent neural network. But we don't have to go with softmax. But for some reason empirically it works very well.
What transformation it is doing softmax this function? So this is a function which we are applying here.
Yeah.
But what is its contribution?
The contribution is basically
Is it compressing, decompressing?
It's normalizing the vector.
Okay.
It's basically like 0 to 1 normalization. You can treat it as such. You can just say like if you have like maybe 10 values and you say, okay, I want to normalize these 10 values, you can just do divide each element by the sum of the elements to standardize, right? But softmax has different characteristics. It's more peaky. Peaky in the sense of like if you have probabilities that are like, I mean, it's exponential. It basically like if there is like a certain difference between two elements in a vector, it just blows it up and says, okay, this, even though this is like low difference, you exponentiate that because you have like an exponential here, and that gives like a very peaky behavior where it prefers to uh, go with like something with conviction
What
rather
are
than
alternatives of softmax?
you can just do like 0 to 1 normalization, like just some normalization. What else can you do? And you don't have to do like softmax at all if you control the score, like the values these scores can take. But any normalization operation is basically what we're looking at.
Okay.
Yeah.
You can also think of softmax as like a way to like choose the weights. Like if you think about like attention as like a weight choosing like operations, then softmax is just like there's like some way that you can technically prove softmax is like the optimal functions to like normalize the weight, but like I won't go into like to math.
Okay.
But in practice, softmax is just very much like used everywhere. So
Yeah.
So it's also maybe something that contributes to divine benevolence. That's not just
Yeah.
sort of works.
Yeah.
So
So we have this, right? Like we have the query key value projections, which are giving us like each of shape d by d. And those are giving also again n by d matrices. And to arrive at the score matrix, we are doing like QK transpose. That's the matrix multiplication, dividing up by square root of d, and then we are normalizing it. And then now what we have is again like an n by n matrix, where the elements are normalized, where each row is row normalized. Each row is like saying, okay, all the rows sum up to 1. Like if you sum up all of these, 1.0, 1.0, 1.0, so on. So, and now we want to, so this is like sequence length by sequence length matrix, but we want again representations of words that act as query for the upcoming epithets. So then what we have is like the output of this attention operation is n by n. And now we have our value matrix, which we haven't used, but like that is what we're actually treating as like the true values, right? When I said, oh, attention is basically computing the weighted sum of true values of the words, this is what I mean. So if the QK transpose gives us like this score matrix, which is n by n, the true values are captured by the matrix n by d, then you can just like matrix multiply these. Because then what this is basically saying is like, this is basically like takes the form of an inner product. I don't know if you can see it. You can see it, right?
Yeah, I can see it.
Yeah. So the true value of design, like we discussed here, it takes like the S act as the weights, the S terms, and these act as like the actual values. So these values are actually the value matrix. So because it takes the form of inner product, and you can see that basically what we are doing is like multiplying this n by n attention matrix by like a value matrix. So what we'll end up with again is n by d. So the total attention operation can be written as QKV. You take the QKV, right? So that's basically softmax of QK transpose by square root D. This is just like for a single head. This is a generalization which we don't have to discuss today. You can read the paper, you can read Jay's blog, and then this. That is the total attention operation that is happening in here, like the masked self-attention. The masked element is basically us saying that these are all zeros. So this score matrix is actually a lower triangular matrix. So, so that's what's happening. Is that clear? Any questions so far?
No.
Yeah.
Yeah, like, oh, like, what's the difference? I'm gonna say masks, self-attention, and I guess just like Gregor's self-attention, or it's
In regular, so yeah, it's a good question. So we are talking about next token prediction, right? Where each token cannot assign a score to the token after it because it technically hasn't seen. Because we're decomposing, like we talked about here. Like the word I only is trying to predict the word am. So there is no way we are going to design an architecture that can look ahead and see the answer.
Oh,
right? Because we want to like explicitly teach it, hey, make the prediction and then we'll tell you what's going to happen, what the ground truth is. And there is a variation of this, like where you don't do next token prediction. There's this thing called masked language modeling. And if you've heard of the architectures BERT,
Birds,
yeah.
But we
Yeah.
Google will, yeah.
Yeah. So all of these architectures are basically like they don't do like autoregressive modeling like this. They actually have these non-zero elements as scores because those models can actually look ahead and like do it. But and that is like a different objective function, and you're trying to get better representations. Birds are used for embeddings, like because you don't really need to construct like a next token prediction task and do autoregressive modeling just to construct better representations for
But
tokens.
Bird paper was written after a transformer. That was the first
yeah,
language model inside Google, as far as I remember.
Yeah, it was probably
They did
written
not
after
use this concept. Or also softmax or things like this.
They did, yeah. They just did not do the masked self-attention. It's like bidirectional attention, and they do masked language modeling. So instead of saying, okay, let's just say like I am a good dog again. In autoregressive modeling, what we said was like I predicts I am predicts I'm a predicts good, I'm a good predicts dog. But what they do is like they mask this. Mask dog. Am. So what they try to do is like they have these randomly masked tokens in a sentence, and they show all the tokens to the transformer and say, hey, like, what is the masked token? What is the identity of that?
Okay, yeah.
And they predict that. And they have these different ratios for like for a given sentence, you drop 10% of the tokens and replace them with masked tokens, and you predict these tokens this way. And in this case, you don't have to do well, you should not do masked.
We are just predicting the next one.
Like this in here, we are trying to predict the next token, but here we can actually show the transformer everything. So this can see this, just like autoregressive modeling, but it can also see this. I mean, this mask token doesn't matter, but so each word is a representation of every other word in the sentence, whether that's behind it or ahead of it, the same thing. So the masked self-attention is basically coming from the fact that the upper triangular portion of this matrix is masked because the model cannot look ahead.
Okay.
Yeah, we are like by design, by construction, we are telling that, hey, like all the scores corresponding to this should be zero.
Okay.
Yeah. So when we actually write the implementation of attention operation, these are actually non-zeros when you compute them, like Aaron was saying earlier, because T2, T1, T2 has a valid inner product, right? Like in the QK transpose, it would come out to be valid values. But because we don't want the model to know, we explicitly go to these entries and say these are zeros. Because we want to take that away. And yeah. And we'll see like there are some constraints that come with like doing this kind of mask because the mask is huge. It's an n by n matrix, right? The score matrix. And n by n meaning like if you've seen Claude release 256,000 context length or Google releasing 1 million context length.
Yeah.
So if you do it naively, then you're basically saying this is a 1 million 1 million rows by 1 million columns matrix. And that is like insanely expensive. Yeah. And no hardware can fit it. So there's a whole bunch of optimizations that go into it. And one of them we'll discuss at the next week's lecture, which is like flash attention, which helps us like not actually like fully build an n by n matrix. But anyway, we won't talk about that right now. But that is the attention operation. QK transpose by square root D, which is basically to control the variance of the matrix multiplication. Softmax for normalization and converting into like a probability distribution. And then you are combining these scores because you want to compute the weighted sum to capture the true value of each word. That is the matrix multiplication with V, which is basically a series of inner products of the scores with the value matrix. And that is the attention operation. Yeah. Okay. So, and the FFN, I'll just like run through FFN because FFN is not complicated at all.
Yes.
So now from the output, I'm skipping over a bunch of these things. They're like the residuals, layer norms. They're very important. Without that, transformer doesn't work. But they're done for different reasons than like just grounding it in intuition.
What is one line like role of layer norm?
What is
I
the
mean, one line if you have to define
Oh, okay.
what it does.
It's are you familiar with just like standardization? Like if you want to convert like a vector into like a normal distribution.
Yeah.
Yeah. So basically that's x minus mu by sigma, right? That's basically if you want to convert it into that's basically a layer norm operation.
So before putting it into self-attention, we are just doing this
Yeah. Let's just say this is like the vector A. All layer norm is doing is A minus A dot mean by A dot standard deviation.
Okay.
This is what layer norm is doing. It has two learnable parameters, which are like scale times plus offset. These are the learnable parameters, but the core of it is just like normalization of each vector. And that's what this is doing.
So we are doing same thing before doing self-attention
And layer norm and before it goes to and with residuals in between. Yeah.
And this is just one decoder block. And this will happen again and again.
Again for like 96 layers, 128 layers. Yeah. And all of these are like initialized with different values. They're like deep copies. They're not just like weight sharing. It's not the same weights that are in layer one and layer two. You know, layer one has different weights, layer two has different weights. All of these. There's no wait time.
Oh, there's no wait time? I thought they.
No, there's no wait time. Yeah.
But you can still wait time during gradients, right? Or
I mean they're weight tied. They're weight tied in the sense of like there is dependence of layer 10's outputs on layer 1's outputs.
Okay, yeah.
But not in the sense of like these are the same weights that go to all these layers.
Okay.
But there is a paper called Universal Transformer, I think.
Yeah.
That tries this. That takes a single transformer layer and just keeps passing the same thing back in. Like it's like a recurrent fashion.
Yeah.
But that doesn't work.
Makes sense.
Yeah. Yeah. But the whole notion is that even like to talk about we're extracting more and more like concepts as we go deeper in the network, it makes sense that each layer has different weights because it's like attuned to different things. It's trying to pick up different things, different semantics, as opposed to something else. So the output of the layer norm, attention, mass, self-attention, and residual, and all of that is just an n by d matrix. And we talked about FFNs being key value matrices in the earlier lecture, like on Thursday. But this is the form that it takes.
So there's a, I think, plus operation for output of self-attention and then layer long, which is then going again.
Yeah, so let me just call this. So you have the input matrix here. That input matrix is cached, it's put aside, and then like you have a copy of that input matrix going to layer norm, and then it goes to self-attention, and the output of self-attention is added to this.
And then it again goes to normalization layer.
Yeah, then it goes to normalization layer. This output again like goes back here and gets added to the output of FFN. Right. And the FFN is basically like it's an expansion and a contraction. So everything in transformer is basically a projection of vectors. You know, like you can describe deep learning as like a way to manipulate vectors. That's all there is. So there is a d-dimensional vector and it keeps changing throughout the layers. And that changing of numbers is basically how it picks up meaning in this n-dimensional space. And in FFN, what we're basically doing here is we're projecting this d-dimensional vector into like 4-dimensional vector and back to d-dimensional vector. That's all there is.
In FFN.
In FFN.
So from 1 dimension to 4 dimension and then again back to 1 dimension.
So each dimension gets split up into 4 dimensions and then contracted into 1 dimension.
Yeah. For expansion and contraction.
Yeah. And for everything, there is like a projection matrix. You know, like again, linear algebra is a tool to convert representations of these n-dimensional vectors. So what is the shape of the weight matrix here? That would project from shape D to 4D.
For D squared, right?
Yeah.
Yeah, because you have to do upwards or like upper chunks, right?
Yeah. So for each element, you're projecting into 4 dimensions, right? So which means there is like and if you have D elements, then you have D times 4D. So this is the shape of the up projection or FFN expansion. And then you have down projection. You want to bring it back down to your D dimensions. And then what is the shape of that?
4D squared.
Yeah, it's again 4D squared. So in between, this is basically FFN, but in between there's a nonlinearity. So if I have to write the code, then I would basically say you have your n by d matrix, which I would call x, and your FFN up projection expansion, which is d by 4d. I will call that W1, and FFN contraction 4d by d, because then you're taking the 4d dimensions back to d dimensions, and that is W2. And then the final FFN x is x times W1 value of W2. This is all that is happening in FFN and in the FFN block there.
So in the class, I think you mentioned FFN. I remember the expansion contraction part.
Yeah.
But you also talked about key value store. So we are not touching any of those right now.
Yeah, because like this is the key projection like matrix. This is W1 is the keys, W2 is the values. Yeah. So that like I'm just like not rediscussing the intuition there. But that's the part, like where FFNs are actually like these key values or the memories of the network, where that's why it makes sense, like intuitively, to have like an expanded dimension in FFN that basically is detecting all kinds of patterns and storing knowledge. And it also has the most number of parameters in a transformer block. Um, and then you have the FFN contraction, which is again constructing the like uh, representations of what is the next token. And it's kind of looking up the corresponding answers. So, and the ReLU is a nonlinearity after the key trigger.
So this is output of block 1, decoder block 1, or this will be input for decoder block 2.
Yeah. So like the output of FFN after the residual add is going to be the input for
this.
which is again like n by d matrix, which again goes to the same series of operations we just talked about.
And these matrices are not saved anywhere. So like in the system,
Yeah, they are
saved. They are saved.
Yeah, because these matrices, like, do you mean n by d matrix or like
each layer? No. So decoder as thinking as one component.
Yeah.
So there's input, there's an output. Then this output will go to the decoder block 2. This output is relevant. Is it saved anywhere or?
You save it for backpropagation, which we will maybe talk about like next lecture or the week after that.
So each decoder step has a output, and that output is relevant. It is saved somewhere.
Yeah, because if you look back at assignment 1, and if you write out like the backward pass for multiple matrix multiplications that are chained together, you do need the intermediate outputs to be saved so that you can use them to send gradients to all the parameters like W1, W2, and you have this like WK, WQ, WK, WV. So there are all these weight matrices that are being tuned in the transformer, and each layer has its own parameters, and these are the activations, you call them, that go through these series of transformations. Yeah, and yeah, that's basically what's happening in a transformer. Yeah, and this is like the key value things that we discussed last week. Yeah, that like the FFN expansion matrix, which has like each dimension is expanded into 4 dimensions. It makes sense to over parameterize that, or like to actually allocate heavy number of parameters, because that's where the memories of all the pre-training data that the model has seen are like stored. It's a bunch of pattern detectors. So it makes sense to actually like expand that. And then you can actually empirically observe that these FFN expansion matrices hold information and are checking for different patterns, whether they're syntactic or semantic, and a combination of them. Uh, and then the down projection is the actual like answers corresponding to those patterns. Okay, when I see this pattern, what do I usually predict as the next token? And that's what's happening in FFN contraction, which is the W2 matrix that we just.
Okay, so expansion is trying to derive as many meanings as possible.
Yeah.
And then contraction is the prediction for each of those.
Yeah, exactly. Yeah. And when you do matrix multiplication, it's a weighted sum of all of these things, because multiple patterns can be triggered for a specific problem. And then you're looking up the answer for each corresponding pattern, and then you're summing all of them up. So it's like a composition of the meanings of different patterns and the answers that correspond to each pattern. And that's the FFN block. And so like fully transformer is basically just that. And there are variations. That's why we talked about MOEs last week.
Yes.
Where we're like, it makes sense intuitively to assign an FFN block to multiple FFN blocks to each transformer.
Can we enlarge this picture?
Yeah.
Yes, refer to it again. MOE1.
Yeah. So this is what you should be looking at. So there is a gating layer, which basically decides. It's like someone sitting at the door. Oh, you're talking about physics, you should go to expert number 1, like FFN block number 1. because that's where all the
How
physics.
would we identify that is expert number one?
It's through training. There's a specific way that you can train MOE, which is a lot more efficient than just training dense model. But I don't think, if you want to get into it.
You can just like have like a linear layer, or just like some people do like just yeah, you can.
So I understand it says like there are multiple experts.
Yeah.
Each expert has a different specialty,
Mhm.
but there's a router layer which is routing, right?
Yeah.
How is that logic defined? Like where to route?
There are different routing logics. There are different mechanisms.
Mhm.
You can just say, hey, like if I have, because this is an architectural decision, like if you say like each transformer block is going to have 10 routers, 10 routers, and then you basically say, okay, I'll have a matrix. I'll have a router matrix that's basically projecting these n by d matrix
Mhm.
into like n by 10 matrix.
Yes.
And then I take a softmax over that, or like see which element of these 10 vectors, of these 10 elements in this vector, get the highest score. And
So
then
all
you
this
route
is
each
happening
vector.
at the pre-training level. This has nothing to do with inference.
Even like if you train MOEs, then it's happening during inference as well. Because whenever you're sending a prompt, and then the router decides, okay, which expert does this go to, and it sends to that expert, and then like again, then you have the adding normalization, and then the same thing again. No, sorry, same thing here. Yeah, this is like not a decoder only architecture, I think. Yeah, but basically that's the idea. Like your router decides where your token goes, which expert it should go to, and then it goes through the FFN expansion contraction with the corresponding expert, and then it's a repetition. You have multiple layers like that.
So a lot of meaning extraction.
Yeah.
And what step I should take for that meaning is actually happening in the FFN layer.
Yeah. And all of that, the attention operation before that is basically how do I construct almost like the perfect query so that the patterns trigger in the memory box, which is
So
FFS.
the name of the paper was misnomer, right?
Attention is all you
Attention
need.
is all you need.
It's definitely not all you need. Yeah, like if you get rid of the FFNs, attention performance drops. Even if you balance the number of parameters, and just like say, oh, I'm removing maybe 100 million parameters from FFN. Why don't I just like add 100 million parameters to the attention mechanism to like balance it? And if you run that ablation, you'll see that pure attention architecture performance is bad. Because FFNs are like a key part of why
I'm trying
transformers
to
work.
correlate this with something I learned, which is known as when we scale architecture, emergent behaviors come in. Where they come from, FFN or
I don't know.
probably FFN.
It's like it has something to do with the residual string, because if you think about like attention as like linear add, or in a sense attentions are like adding informations into like the stream of like context that you have, right?
So at the scale, are we asking better questions? Or at a scale, we are connecting a lot more dots in expansion, contraction.
It's hard to say at like what, because there are like the papers that say, oh, like until 7 billion parameters, this benchmark actually doesn't improve at all. Maybe it gets worse, but there's like a threshold beyond which you suddenly see improvements. So what about that is not actually leading monotonous increases, and there seems to be like almost like a switch, right? So that I don't think anyone knows the exact behavior that's leading to it. You can say that like when you have too little of like parameters or neurons in the FFN expansion, we also talked about superposition in lecture 3, where like multiple concepts are being stored, forcibly compressed into these 4-dimension, like 4D neurons, right? And that's not enough. Like if you beyond, maybe the hypothesis is that beneath a certain scale, that compression is almost like self-defeating. It's like, oh, like you're superimposing too many concepts into one neuron, that there is some forgetfulness problem, and it's not being distributed across enough neurons properly that you're unable to see performance gains. So that could be one of the hypotheses where like, we don't know if that's true or not, but that's just like most of the field is again like just like spitballing about like, oh, what could be happening? Let's just test it out. And yeah.
Also, like grokking is an property that emerge that like after a certain runs of train, the
Mhm.
model would just improve, right? So like
Mhm.
in a sense, we don't really understand why the model grokked per se.
Mhm.
So I think like that's still like a ongoing questions
Yeah.
in Turk specifically.
Mhm.
Yeah. But honestly, I feel like to understand how the model grokks, then we would probably have a better understanding of like how we can map like features and
Yeah.
control like concepts. So
Yeah, if we understand the mechanism well, that also means we'll be able to train smaller models much more efficiently, or even figure out better ways to teach these models rather than showing them the entire web. Or maybe there's a way to disambiguate, or like disentangle uh, the knowledge base, which is FFN, from the actual querying mechanism.
Yeah.
Maybe you can. There was this paper called Retro.
Distribute them into different
Yeah, maybe you can have like a different architecture
Different
that
architecture.
doesn't need to like see trillions of tokens to get state-of-the-art performance. There was this paper called Retro from DeepMind, which basically like dynamically for every query, even during pre-training, would fetch from the entire database of like pre-training corpus and would look for documents that are similar to it and append those to the current prompt and train. And I think it has like still a lot of potential, but no one can build that infrastructure. The infrastructure to build retro is like incredibly complex. So which is why no one has done it at pre-training scale. But I'm hopeful that we'll be able to disentangle the FFN key value memories and the actual querying mechanism, which is the secret of attention.
in separate components.
Yeah, or like at least design efficiently. Yeah, these FFNs. That's
It's just nobody has tried to dissociate them because this thing worked.
yeah, this
It
thing
continues-
works.
They learn it worked, they continue scaling it.
Yeah.
But then more work is required to identify how to make it more efficient.
Yeah, there's so much stuff.
No, I should say like at the moment like everybody uses this
Yeah.
same architecture for like all the models, even the vision, like audio, everything, right? Like multi-modals. They're all the same. They're basically the same actually, right?
Mhm.
conceptually, yes.
Essentially, but what would be the like main difference when they say like uh okay, how would they come from this transform architecture to like okay, let's do the like vision model. How would you
Like into it, multi-model or video?
multi-model, let's say, or like
You're saying how do you apply this to multiple domains or
yeah.
Oh, okay.
How would you start like reasoning about it? Given that
How do you start reasoning about
Yeah.
applying this architecture to multiple domains or
Yeah.
it's I think the core intuition is still very valid, which is like, oh, like there's a bunch of memories about the world that you would want your system to have.
Mhm.
And the core intuition is again like language, it has images, voice, audio, like all of them share similar properties
Mhm.
of like I don't know if you're into like music, there's the people say there's no such thing as a wrong chord. You can play chord that sounds super dissonant, and on its own it sounds horrible. But if you place it nicely, like if you have it in the right context, even the most dissonant chord can sound right because like it's preceded by something that makes sense thematically.
Right.
So you can make the same argument for different modalities like this and say like the true essence of something atomic actually depends on the context in which it sits. And that is basically what attention is doing.
Okay.
So you can apply that to images because like a patch of an image can depend on like every other patch or patches that came before it. Or like audio, like like everything like the perception of the current thing depends on everything that came before it. And yeah, like this philosophy is applicable to like basically any domain, which is why it makes sense for transformers to be applied like everywhere. Yeah,
Yeah, very scale.
yeah,
Like even at the like on agentic like workflows as well.
yeah. Everything is like like I said, anywhere you see this, I'm taking like an action right now, but the action I'm taking right now kind of depends on the actions I've taken before. It's such a broad framework that you can apply this to so many things. Yeah, and especially to agentic frameworks, maybe it's even more compatible.
So I have a similar question. I did not ask in the class in 2 days before because it might be going different direction. So we have this reasoning models.
Yeah.
Where input is given into the output. Is the same as next token prediction?
Yeah.
The same concept, just they are trying to use words. Here they are doing it for traces.
Yeah, like post training is not, I wouldn't say it's doing like next token prediction in the same sense of like pre-training.
It's next trace prediction, and then last two traces will go into the input, and then
yeah. That is auto-regressive because yes. Even like test time compute, which is like reasoning models, same thing. You're basically just forcing them to say, hey, like think before you answer, and they like emulate like thinking trace. Like, oh, this is this, this is this. So let me like put these things together, and then it's actually starts answering. So they were trained that way. Like these reasoning models, they were shown. I think I don't know how they captured all of these chain of thought traces, but yeah, even before reasoning models were a thing, people wrote papers that talked about, oh, like chain of thought seems to improve the performance of these language models, which is basically like adding your prompt. If you're asking a language model, hey, can you give me the answer to 2 plus 2, but think before you answer, then it like you see answers like, oh, okay, 2 is 2, and I'm adding.
I ran a query like on GPT-5 yesterday, and the question was simple: how many days Mr. Carney has been Prime Minister in Canada?
Yeah.
And the model was like, oh, is he Prime Minister? I don't think he's Prime Minister. Like, he's not Prime Minister of London, not Prime Minister of Canada. Then he said, let me use the search tool.
Yeah.
Then he searches the search tool. Then he figures out, oh, he is now actually a Prime Minister.
Yeah.
And then he's actually changing his answer and calculating it.
Yeah. So that's tool use, and
it builds also on the intuition of like, there's a few paper when they do like zero shot, few shots like prompting. So they look into like why few shot prompting works for a specific domain task. So like that. So like idea of like, oh, reasoning, so like coming in, so like
this one, number of days.
Why?
So initially it's like, oh, he's not the Prime Minister.
Yeah.
It's not as per my training data. Then you actually search for it.
Yeah.
And then you figure out there's a discrepancy in my targeting.
Yeah.
And
so these models, like, you know, like if I'm at a big lab and I'm launching a training job, like I scraped a whole bunch of data and I process it, but I could only process until mid 2024. Like that's my knowledge cutoff because that's all the data I have. So I don't have knowledge on up-to-date events, which is why search is so important. So if someone asks a question like this, then the model is like trained to be like, okay, this is beyond my knowledge cutoff. Someone's asking about current events, so let me trigger a search, and it like has like a Brave integration or like Azure integration. Sorry, not Azure, Bing integration, and then it searches, and then it looks at the results, and then it says, okay, so these are the current events, so let me update. And
But even for it to search, it has to arrive to a right question.
Yeah.
And that is also a process.
Yeah. So there is like the search thing is like actually some people use like a query generation system separately, where like you type in a prompt and that goes into not just the language model, but it goes into something else. Does this require a search? And if it says yes, and then there's another model that generates the search query, because there is a search query optimization is also a thing, right? Like, I mean, it's increasingly becoming maybe irrelevant, but you know how people do search engine optimization, because the search queries for which your company comes up for might be different from what people are actually searching for. So you basically tweak a whole bunch of things. So the query generation phase is also about like, how do you construct a query that is friendly to all these popular search engines like Bing or Google, and whoever else is like DuckDuckGo or whatever. So they generate queries that are good for the search engines and have good recall, and then include that information in your answer. Yeah. Anyway,
very side question, but
yeah.
What's like your definition of like agents? It's like that word has been going around.
It's a buzzword like
A lot. Like
we need to reframe it and ask it.
Oh, what is a
like? Do you think like what people call agents nowadays makes sense, or is it or it's just a buzzword for marketing purposes?
I mean, it makes sense like conceptually, because like if the LLM is taking actions on behalf of you,
Yeah.
then it makes sense to say, oh, it's being agentic because like it has agency now
Sure.
to do stuff and not just like blabber,
Okay.
you know. And so any tool use is arguably also agentic because it's doing things that you can do. Earlier, like before the tool use was a thing, models would just give you the code,
Right.
you know, like, oh, this is the code that you would need to write. And now you just like go do that. And now they actually run the code, they look at the bugs, or oh, there's a lint error, let me fix that.
Right.
So all of these actions, they're trained to do that,
Yeah.
obviously.
How are
but,
they trained for tool use?
Uh,
Like is in the training data or
Yeah, it's in the
architecture is the same? Like
Yeah.
the architecture which
most likely during the post-training phase, all these labs have like curate data for that and say, oh, if someone's asking about arithmetic, it's much more reliable for you to use like a Python tool.
Yeah.
So, and this is how you would use a Python tool. And any tool use for general tool use, this is the structure in which you will need to produce the JSON to call the tool, like that's like MCP or something. Yeah. But yeah, there's a specific format in which all of these LLMs are trained to use tools or call tools, and they're trained to do that. They were shown this format many times, and that's how they can use these tools and recognize when to use them and not to use them, etc.
one more question relevant to this one.
Yeah.
So this flow, like if I have to map it into a flow, it is for pre-training stage.
Yeah.
Now the model is trained fully. We have done what will we do? Like what would be the steps during post-training and inference? Like will it be same, similar, or 30% same, 20% same?
Inference is a bit different compared to training.
Post-training is like
We have not thought. I think it's coming in the classes.
Yeah, post-training is later, but we're just talking about like the components that go into pre-training. I mean, technically, we are not even talking about pre-training yet, right? Like, in a sense, like the assignment 3 is actually your pre-training, like a much smaller
The
model.
inference is a separate topic then.
Inference is a separate
Oh,
topic. Post-training is a separate topic. Yeah.
Pre-training is a topic in itself.
Yeah. So everything has like so many. It's not possible to. We have 12 weeks, right? So it's not possible to cover all of these things because everything has so much, like the whole field is moving so fast. So it's just impossible to cover this in 12 weeks, everything that goes into it. But which is why one of the core motivations or anchors for this series is like you walk away with the right questions so that you engage with what you find interesting. Because it's impossible to cover everything where you're autonomous. And which also means like you dedicate significant amount of time outside of the lectures to actually be able to do this stuff. And perhaps like one of the things I'm learning during this series is like I was a little bit too lenient with the prerequisites. And I think for me, what was more important is like, is someone willing to learn? And that is what I filtered for. But sometimes I didn't even look at how much time they're willing to commit. If it's like 3 hours a week or like 2 hours a week, especially if you're coming from a background that, like not a heavy math background, not a heavy coding background. It's almost demotivating. If that is your time threshold. But hopefully some of the intuitions still make sense. And hopefully you find the content itself and the questions itself meaningful enough that you're willing to just do this for fun.
I'm having a lot of fun actually.
Okay.
Yeah.
I'm glad. I like the live stream. Those are cool.
I've been trying to.
Yeah.
No, today was fun as well, like QKV and all those things.
Yeah.
Which we were not able to go deeper in the class. I think this recording will be very useful.
Yeah, I didn't talk about like later on. We briefly talked about residual connections. I mentioned in lecture 3. All of these things I couldn't even do a very good job explaining the intuitions because they're rooted in like empirical experiments, and which is why I was like, some things you have to take for granted. You can try to hypothesize why they work, but you would never be able to prove it. At least at this stage.
Yeah, I guess I brought this up with you before, but I guess like if you need help with like lecture hours or like TA hours and stuff.
Let's do it. Like,
if people want to like come in and question, I can try to help.
Let's set something up. Like, I would love to get feedback in general from you guys. Like, I would love for Slack to be more active. Like you've been posting stuff. Like, just post the code. Like, and you've been very active as well. So I would love for Slack to be more like thriving.
Yeah.
And also to have like all these parallel sessions for like
Yeah.
just talking about random stuff, collaborating on things.
Yeah.
Additional idea for like potential post lecture like activity would be like to have some like test level kind of like question with multiple choice or something where you sort of like go through it and like with each question you sort of like refer back to the like lecture material, etc.,
Yeah.
etc., and try to like read it through and yeah, like without like using a lens,
Yeah.
essentially, and
Yeah.
and sort of highlight the key questions. Because,
Yeah.
yeah,
You know that.
what like you would say is like key information, so sort of like
Yeah.
highlights.
Like this was very useful from the lecture because I
Okay.
knew about the paper,
Right,
but I did not know about the different concepts.
Right.
And today my goal was just to go and understand different concepts because then
That's
I'm able to
nice.
connect the dots here.
Yeah.
Yeah.
Yeah, we can do that. I also want to leave more time after the lectures because like
That's fair.
yeah, I usually reserve stadium for 2 hours, but the lectures are like turning out to be long. That there's not enough time for people after to engage with the questions or even talk to each other about like things that they haven't understood.
Because I felt like people just sort of like went there, listened to it, and then left.
Yeah. Especially last lecture, I think that was like more.
Yeah, it was a lot of moving part. It's
Yeah.
very dense.
Yeah.
Yeah,
And I didn't even like I almost left half the lecture out last week.
I see.
Yeah.
Okay.
Because I was supposed to talk about like positional embeddings at length
Yeah.
and also the pre-norm versus post-norm.
Oh yeah.
Because if you go to the tsfm.ca or like /lecture 3, the
Yeah.
first visualization you
It's
see
like
is actually for the
makes sense.
gradient norms and why are they bad. Yeah. Let's stop the recording now. Hope anyone watching this found it useful.
Uh,